I already briefly mentioned that there was two approaches to quantum field theory, the canonical quantization and the many-path approach. So what are, in few words, the differences between these two approaches? In the canonical quantization, what you do is you take an equation for classical fields. For instance, the Klein-Gordon or the Dirac equation can be expressed for classical fields, and then you quantize it. So what it means is a bit more than just putting a hat on top of operators. It's also imposing some commutation or anti-commutation relationships. This is a historical way. Most books start with that, like Peskin and Schroeder. Also, this is not necessarily the most intuitive way. Many-path approach is based on the many-path formulation of quantum mechanics proposed by Feynman in 1948. This approach can be generalized to the case of fields, and we need for that to require Lorentz invariance. And this is a starting point for some recent book like the one by Z. So historically, there is three ways to introduce quantum mechanics. Heisenberg introduced his version of quantum mechanics in 1925 by rediscovering the mathematical tool of matrices. A year later, Schrödinger introduced the wave equation. Both approaches have been merged by Dirac a few years later, showing that they were the same theory. And a few years later, after the war, Richard Feynman proposes many-path approach. I don't know if this is a common features of all Nobel laureates, but as you can see, these three scientists are very proud of their forehead. So how does it work? Imagine you're in class and you have a professor um, telling you about the two-slit experiment. So you have a particle initially at time t0 at the point S and ending up at time t on the screen in O and going through one or both of the slits through a screen in A1 and A2. And the professor tells you that to get the total amplitude to go from S to O, you have to sum the amplitudes associated for each path. So imagine you have a student who raise her hand and ask a question, what happens if we put a third hole in the screen? And the professor says, obviously the answer will be that we will have to sum over three paths now. So now the student raises her hand again and asks what happens if I put another screen with another set of holes, and then the answer is obviously that you have to take all possible combinations starting from S to each of the first holes and going through each possibilities for the holes in the second screen, etc. And now the student raises her hand again and say, what happens if I remove all the screens? Or if I put so many holes that there is no screens anymore? And the answer is a bit less intuitive now because what you have is that your particle initially in S will explore all the possible trajectories before it reaches O. This is not yet the many-path formulation because here we are still talking of trajectories where the vertical and the horizontal axis denote space, but a path, strictly speaking, connects events in space-time. So we should have the vertical axis still denoting space, but horizontal axis denoting time. And in many-path formulation of quantum mechanics, the total amplitude to go from the event S to the event O is obtained by summing the amplitude for each of the paths connecting S and O.